let me just welcome everybody. Thank you all for coming. I'm Ismar Volich, and I'm the director and co-founder of the Institute for Mathematics and Democracy. And we are the ones putting on this event. And we generally have at least one or two events per semester where we try to feature our fabulous, fantastic students who do research with us. And so today, what you'll hear about in these short talks, we'll have 4 short talks on the topics of the summer research of a few of our summer students from last summer. IMD, for those of you who don't know, is an organization that's trying to do more with research and education and outreach that lies in the intersection of math and politics. We do lots of things. Most of our things are student directed. So students, if you're out there and you're interested in getting into this very exciting interdisciplinary understudied field of math and politics, you should talk to us, send us some emails, and we'll try to get you involved in our research or sort of education effort or outreach efforts. I should also thank the math department that really sort of supports us, those of us faculty who do this IMD stuff, and also the wonderful students who are really without them this would all fall apart pretty instantly. So thank you to students, and I'd like to thank Wellesley College, that is ultimately the one, the organization that supports us and helps us put these things on. I'm going to turn the floor to Professor Cheng, who is a co-founder of IMD and sort of my partner in crime in all this, and he will moderate the first couple of talks. I'll be around as well for the whole thing, and then I'll moderate the later 2 talks. You're free to sort of leave and come in anytime you want, and I hope you enjoy the talks. Yeah, so Stanley, take it away.
Hi, I'm Stanley Chang. I'm one of the co-founders of IMD. For those of you who are my students here for those of you who are my students right now, you only have to stay for 1 talk. You don't have to stay for the whole thing. We welcome you to this event, and we'll just get right to it, right? So Eliza Zizka, class of 2022, will be giving our first talk. Her title is called A Fair Dictatorship, Social Choice Theory and Category Theory. Eliza, do you have permission to put up your slides?
I believe so. Let me see.
And while she's doing it, I'm sorry, we should mention the usual sort of protocol stuff. We are recording this, and we will post these talks on our IMD website, but only the speaker will be visible, and if you guys have some questions later, then you might be visible. If you don't want to be visible, you can turn off your cameras, the usual stuff. But yeah, hope that's
Can everyone see the slides? Yes.
So Eliza, you'll have 20 minutes, and nearing the 20 minutes, I will try to wave you to finish.
Okay, awesome. Sounds good. All right, I'll get started. Hi, everyone. Thank you for coming. As Professor Cheng said, my name is Eliza Zizka. I'm a senior, and today I'm going to be talking a little bit about my research into social choice theory and category theory, which I will explain what both of those are, and kind of what I did this summer, and also what Professor Volich and I are working on right now this semester. So a little bit of background. Social choice theory is a field at the intersection of math, politics, and economics, and it's really focused on studying how a group of individuals can make a collective decision through voting. So we will be looking specifically at one type of voting method, one type of voting method called ranked choice voting. And the idea behind ranked choice voting is that when voters get up to the ballot box and they see that list of candidates, instead of just choosing one candidate, as most of us are probably used to in voting, they're actually going to rank in order of preference all of the candidates. So they're kind of voting some vote for everyone. And there are different voting methods within ranked choice voting that will then take all of those lists of preferences and produce a final ordering based on those. And from there, you can get the winner or winners. And recently in the news, you may have heard of one specific type of ranked choice voting is instant runoff, which was used last month or the month before in the New York mayoral primary, and also was on the ballot last year in Massachusetts, although it did not pass. And an example of when we have a set of ballots in ranked choice voting, it's called a profile. So you can see at the bottom of the screen, we have an example of a profile. That's where there are 4 candidates in this case, A through D, and 6 voters, and each of the voters has ranked in order of preference all of the candidates. And then depending on the voting method you were using, you would take these 6 ballots and then you would create that final ordering. I was specifically looking at Arrow's impossibility theorem, which is a theorem that relates to ranked choice voting. It was created in 1951 by Kenneth Arrow, who is principally an economist, but also kind of one of the founders of social choice theory. And he published this theorem that essentially says there is no perfect ranked choice voting method that satisfies a specific set of desirable criteria. And these criteria you can see up on the screen. I'll go through a few of them, kind of the most important ones. But basically, these are things that we would expect a fair voting system to have. So the fact that we can't have all of them is clearly a problem. So a few of them, for example, the Pareto condition is something that says that if all voters rank a candidate A over candidate B, then the final ranking should have A over B. And that's something that just makes sense, right? And then another one would be the independence of irrelevant alternatives. So the idea behind this is that we can't have like a spoiler candidate, which basically means that third-party candidate who can influence the relative preference between 2 other candidates. And we know in our kind of normal voting plurality, like for presidential races, that this happens all the time. It has happened in recent political history, but in an ideal ranked choice voting method, that wouldn't be possible. And in fact, the Pareto condition and independence of irrelevant alternatives are kind of the 2 we focus on, because these are two criteria that we would want in any fair ranked choice voting method. And what Arrow's impossibility theorem says is that the only one that has both of those is actually a dictatorship, which is clearly not fair in and of itself. And when we say dictatorship, what we're saying in this sense is that there is one voter for whom the resulting ranking always matches their ballot, no matter how they vote. So none of the other voters, their input doesn't matter into the final ranking. And Arrow's impossibility theorem is very interesting because before it was published, social choice theory was kind of just on the margins of political theory and economics, but it was this theorem and kind of the exposing of this paradox that allowed social choice theory to become such a fully fledged field, because it brings up this question of, if you can't have all of these criteria, then which ones are you going to choose? And how do we decide which ones are the most important? This summer, I was studying Arrow's theorem through a field of math known as category theory. And category theory basically generalizes the constructions of other mathematical concepts into structures called categories. And then these categories are made up of what we call objects and arrows, which are the maps between the objects. So you can see on the left of the screen, this is a typical category theory diagram. And we have X, Y, and Z, which are our objects. So they could be sets, they could be elements, they could be like mugs, anything. And the idea is that then we have like F and G would be our arrows between these objects. And an important part of any category is that you have to have composition. So if you look at G composed with F, which is the arrow that goes from X to Z, that has to be an arrow in our category. And that's one of the requirements. And some of the other concepts of category theory that we'll use is the idea of a Hom set. So if we're looking at the Hom set of X and Y, that's basically all of the arrows between X and Y. So F would be an element of that set, but there could be others in addition. We also talk about functors, which are maps between categories, and then natural transformations, which are maps between functors. And what's really amazing about category theory is that it provides this general abstract framework that captures all of these mathematical concepts. So when you have some result or theorem in category theory, it actually can be applied across all of these fields. And so it's very much this like unifying idea that allows us to kind of almost translate between different types of math. And you can see at the bottom of the screen, this is just a table that shows maybe some constructions that you're familiar with from your math classes and how you would formulate those in category theory and what the objects would be and what the morphisms would be. So the first goal of my project this summer was to study a paper from 1980 by Hans Keiding titled "The Categorical Approach to Social Choice Theory." And we wanted to understand, basically in this paper, Hans Keiding is using category theory and category theoretic structures to reformulate Arrow's theorem and prove it. So we wanted to understand how he uses that and what the framework is. And I won't go into complete detail because it was a lot of decoding and looking things up and trying to figure out what was going on. But I'm just going to run through kind of some of the basic outline. So essentially, Keiding started with X, which was his set of candidates. And he created a category off of that by basically taking the objects were subsets of X. So we're little groupings of different candidates. And then he had a set of voters, A, which lived in another category. And the functor that was relating X and A was this composition functor. So what it would first do is you would take a set of candidates and you would map them to their orderings using this functor P. And then from there, you would map those orderings to specific voters and to the set of ballots between the voters and those orderings. So essentially the whole process, if you started with a set of candidates and you put it through this functor, you would end up with a set of ballots. So that was one of our functors. And then the other one was kind of just this general functor that basically takes all of your candidates and gives you a winner. And once we set that up, you're able to create a voting method, which we call in social choice theory a social choice function, as a natural transformation because it's a map between functors. And so it's going from this one functor that's giving you your profiles, and it's going to the other functor that's giving you your winner. And once you set this all up the way that he did it, he was actually kind of like racking up those criteria that we saw about Arrow's theorem. And the final result, you kind of get Arrow's theorem basically falls out of the Yoneda lemma, which is this really big result in category theory. This is an image I created to kind of illustrate how Keiding was using the Yoneda lemma. So essentially what the lemma tells us is that there's a relationship such that for every voting method, mu, so that's these arrows that are going from the top to the bottom. So for every mu, there is a specific voter Z such that the end result of our election always matches Z's ballot. And that's exactly how we categorized our dictator. So it's pretty amazing that you can kind of take these like sets and arrows and this theorem in category theory that might seem completely irrelevant and actually use it to get this result that's about people and voting that we see in the real world. And it was this process of Keiding using category theory to explore Arrow's theorem that kind of motivated the second part of my project, which was to look at another social choice process using category theory, and that's apportionment. So the second part of my talk is going to be focused on apportionment theory, which is basically deals with how we can divide a set of House seats among various state populations in the fairest way. And the way I was most familiar with apportionment was with the US House of Representatives. So that's basically 425 seats, 50 states, every 10 years, which this just happened with 2020, we get the census, and that gives us the populations of all the states, and the seats can be reallocated among those states. And apportionment of the US House has actually been debated since the founding of the country. A little fun historical fact is that the first ever presidential veto was when George Washington vetoed Hamilton's apportionment method in favor of Jefferson's. And we'll get into a little bit more of the math behind that political decision later. But that kind of speaks to how important this aspect of math is into our daily political lives. So a usual apportionment situation, you get a House size, you get a number of states, and you get the populations for each state. And then your output is the number of seats that each state receives. And actually, as I just said, like we're thinking of apportionment usually as like seats and states, but another way to think about it is in terms of parties and proportional representation. So especially in other countries, you can think about the citizens of the country will go out and vote for a party they want to represent them. And then based on the votes that the parties get, they will get seats in the legislature. And even though these are very analogous processes, there's kind of different methods to think about them usually. So it took us a while to make that connection. But when we started to think about if you like live in the state of Massachusetts, for example, it's almost like you're going out and casting a vote for Massachusetts. for like the party of Massachusetts, and then the total votes for Massachusetts are the same as the population of Massachusetts, and then we can assign seats to Massachusetts based on that. And so once we made that connection, it was like this light bulb moment where we were like, oh, maybe we can use these ideas of voting that we already have in category theory to kind of approach that. So that was pretty exciting. We'll talk more about that later. So we're going to look at an example to kind of understand why apportionment is such a divisive issue. And in this example, we have 10 seats to divide among the 4 states. You can see the state populations in the table below. So the first step is that we want to calculate each state's fair share of seats, and we call this the quota. Basically, what we're doing is we're finding the fraction of the total population that each state has, and then we multiply that by the number of seats in total. And when we get that, you can see this is in the 3rd column. So basically, the root of the apportionment problem lies in the fact that these quotas are very rarely going to be integers. But we can't just like go around dividing representatives into fractions because they're technically people too. So what we have to do is figure out a way to deal with these non-integer numbers and get integer seats out of them. Most apportionment methods will start by taking this quota and rounding down, because that gives you the minimum number of seats that each state would have. But we can see that even in this example, once we do that, it only adds up to 8. So we still have 2 seats that we have to figure out who should get them, where should they go, and what's the fairest way to distribute them. And that's where we get different apportionment methods, is in deciding how to allocate these 2 remaining seats. One specific method that we can look at for how to deal with this is called the Jefferson or Don apportionment method. It was actually separately devised by Thomas Jefferson in 1792, and then by Belgian mathematician Victor Don in 1878. And so they actually had they framed their processes a little bit differently, but the math is essentially still the same. And we're going to actually look at Don's method because it was the way that he constructed it that led us on the current path we are now for our category theory approach. So that's going to make more sense later if we look at it this way. And the basic idea is that you are performing however many rounds you have of seats to distribute. So in this case, there are 10 seats, so we're going to perform 10 rounds. And each round, you're only giving away 1 seat. And the way you decide who gets that seat is that you have to perform some sort of calculation on the populations. So in Don's method, what you're doing is you're taking each state's population and then you're dividing it by the number of seats it has at the beginning of the round plus 1. So in the first round, everyone has 0 seats. So you're going to divide everything by 1 because 0 plus 1 is 1. And you get what you can see in the round 1 column. And then the way we decide who gets that seat is by whoever has the highest number, whichever state has the highest number. So in this case, it would be state D. And then round 2, A through C still have 0 seats. So we're still going to divide them only by 1. But this time state D already has 1 seat. So we're going to divide it by 2. And you can see we kind of do the same thing again. For round 3, state D gets the seat. But in round 4, we're still dividing A through C by 1. But this time state D is being divided by 4 because it already has 3 seats. And so that this time state A has the highest number, so it's going to get that seat. And we keep on doing that until we've given away all 10 seats. What I really want you to notice about the last column, which is our final apportionment method, is where those 2 last seats went. So those 2 that we were trying to figure out how they should be allocated, they both went to state D. And what's interesting about that is if we go back to the quotas, we can this kind of speaks to like one of the ways that we measure fairness about apportionment. Because state D's quota was 5.8, which is obviously between 5 and 6. And one of the ways to think about fairness in apportionment method is that the seats given to a state should be it should be its quota either rounded down or rounded up. So ideally state D would get 5 or 6 seats, but actually it's getting 7. And so that is what we would say that Jefferson's method violates quota because it's giving state D more than its fair share. And interestingly, this speaks to that veto from earlier, because the reason that Washington chose Jefferson's method over Hamilton's is that it actually tends to favor these larger states like state D. And at the time, Jefferson and Washington were both from Virginia, which was one of the largest states. in the country. And so they wanted to choose the math that would give them more representation in Congress. And that's why they chose Jefferson's method. This inequity kind of speaks to the Balinsky-Young theorem, which is basically kind of almost Arrow's counterpart in apportionment theory. It's another impossibility theorem, and it deals with neutral apportionment methods. So a neutral apportionment method just means that it's not doing different things for different states. We're just doing the same process to all of the states. And if we're looking at neutral apportionment methods, Balinsky-Young says that either any apportionment method would either violate quota, like we just saw Jefferson's did, or it would violate population monotonicity. And population monotonicity basically means that if you're looking at each state's population growth, that if a state has faster population growth than another state, it shouldn't be able to lose a seat to that state, because it doesn't make sense that you would grow in population, but you would lose representation. That doesn't seem fair. But again, we get this contradiction where we can't have both. And so it again speaks to this idea of which one do we choose? So this semester, we have been working to recast this theorem in category theory to kind of use this framework where we have machinery to make connections between the abstract and the real. And actually, up until last week, we had still been grappling with even like figuring out how to represent the process of apportionment and with categories and functors. So this is pretty exciting to me because it's kind of new and it's what we've come up with. And we're just going to run through it a little bit to kind of give you an idea. But what we decided is to work in the category of z, which is our integers. So z squared to the n. And that sounds like a little bit of a mess, but what that basically means is that our objects are sets of n ordered pairs, where n is the number of states we have. And the objects that we especially care about are these ordered sets of ordered pairs, where each ordered pair is a state population together with the number of seats that that state has. So when we think back to that round that we were doing, that was the information that we really needed, was what is the population of each state and how many seats does it have? So if our objects already have that information in them, then we can perform this process on them. And that's where our functor comes in. Our functor would be from this category to itself. And what it does is it basically takes one of these sets of ordered pairs, it performs some sort of calculation. So example of the Jefferson's method, it was dividing by a plus 1. And then it determines which state should get the next seat. So again, that was the one with the highest number. And then it maps to a new object in this category that is exactly the same, except for the only difference is that one state has one more seat than before. And so that's how we would represent one round of giving out one seat. And we can do that h times, we can compose that functor h times, and that would give us our final apportionment. And so that's kind of the first piece, is kind of representing this process, but now we want to think about how do we represent Balinsky-Young theorem using figuring out how to show population monotonicity and that sense of quota. So that's kind of the next step that we're looking for, is trying to move on to showing, we think that we already have population monotonicity kind of baked into the way we defined it, but then we would want to show that every time something is population monotone, it would violate quota. So that's kind of the first goal of looking forward, is to formulate and hopefully prove the Balinsky-Young theorem using category theory. And then moving on from there, another way that this project could go, or other projects off of it, would be really interesting to use other major category theory results like the Yoneda dilemma and apply them to social choice theory to yield new information about elections and voting and apportionment. And then also something that's kind of related that someone could think about is social choice theory and game theory, and how they could be explored through category theory. So thank you so much for listening, and thank you to Professor Volich and the Science Center Research Program for making this possible.
Thank you very much, Eliza. We have maybe time for one question. I can't see everybody, so I don't know how to use can't see the raise hand function, can I? I don't know. If anybody has a question, just go ahead and shout out. All right, Eliza, it seems like you're off the hook. Thank you so much. That was a great talk, very interesting stuff. We will recess for 3 minutes and then come back for the next talk.